Okay, good morning all. We'll start with the today's class. In today's class, we'll be discussing the last part of the flip-flops before we go into the applications of flip-flops like counters, registers and all. One more important part of the flip-flops we are going to discuss in this class, and that is about alternate representations of the flip-flops. So already we have studied 4 different flip-flops, and we have seen the truth tables of these 4 different flip-flops, how this flip-flop behaves, and also we have seen how exactly each of the flip-flop functions for the different inputs whenever the clock is applied. Now in this class we are going to discuss about the alternate representations of the flip-flop. That is a very important part, that is how we can represent a flip-flop by its characteristic equation, and then the excitation tables and the state diagrams, which will be useful for you when you study the counter design. In this last part of this module as well as in the next module, when you study the design of the counters, there definitely these excitation tables as well as the state diagrams plays a very important role, and they will help you in designing those counters. So we'll start with the characteristic equation. What exactly you mean by characteristic equation, and how we can derive the characteristic equations for each of the 4 flip-flops. So if I explain you how the characteristic equation can be derived for one flip-flop, very easily you can derive the characteristic equations for all the remaining 3 flip-flops. So in the previous class, we ended our discussion with the JK flip-flop and T flip-flop, if you remember. So I will start with what you mean by a characteristic equation and how we can derive the characteristic equation for the JK flip-flop itself. All right, and then similarly, you can derive the characteristic equation for the SR flip-flop, D flip-flop, and T flip-flop. And once the characteristic equation are derived, very easily you can get what is called as excitation table. Okay, so what exactly you mean by a characteristic equation, right? So as the name itself indicates, a characteristic equation is a Boolean equation which describes the flip-flop functionality, or it describes what will be the next state for the given flip-flop with the given inputs. That is, if you have a particular type of flip-flop and if you know what are the inputs that you are going to apply to that particular flip-flop, what will be the next state of that flip-flop for the given inputs will be very easily obtained using the logic equation, and that logic equation itself is called as the characteristic equation of the flip-flop. So characteristic equation characterize the flip-flop next state for the given inputs. Of course, it is a sequential circuit, so it will take care of the previous output and it will give you the next output for the given inputs. So we'll try to derive this characteristic equation for the 4 types of flip-flops which we have studied. That is SR flip-flop, JK flip-flop, D flip-flop, and T flip-flop. So first, I will explain how we can derive the characteristic equation for the JK flip-flop. Then on the similar line, you can derive it for the SR flip-flop, and lastly, you can derive the characteristic equation for the D and T flip-flops, which are having only single inputs. Okay, so I will start with what is the characteristic equation for the JK flip-flop. I hope the board is visible. Is the board visible?
Yes, sir.
Okay, so we'll try to derive characteristic equation for the JK flip-flop. So to derive the characteristic equation for the JK flip-flop, first we should know the truth table of the JK flip-flop, which we already studied. So quickly, I will write the truth table of the JK flip-flop here. Right? I will consider a clock, then I will take J input, K input, and the next state Qn plus 1 I am writing here now, Qn plus 1 indicates the next state and Qn indicates the present state. Just to differentiate between writing only Q, I have added a suffix now Qn plus 1. What Qn plus 1 indicate? The next state of the flip-flop, and Qn will be the present state or the current state of the flip-flop. And we have derived the truth table, and we have seen that when clock is absent, irrespective of J and K, the flip-flop remains in previous state. So I have written here Qn now. Means Qn plus 1 will be Qn when clock is 0. Similarly, when you apply clock, based on the values of J and K, the Q output will change, and accordingly the flip-flop will be in one of the states. So 0, 0, 0, 1, 1, 0, 1, 1. What happens when you apply the clock and J is 0, K is 0? What will be the state of the JK flip-flop? Yes. When you apply J0, K0 along with the clock, what will be the output Qn plus 1 or Q output of the flip-flop? Yes. It remains in what again? J equal to 0, K equal to 0 makes the flip-flop to remain in what? Previous state, so that is Qn. If you want, you can write the one more column called state, and you can write that as no change state. Similarly, can you tell me anybody? When you apply clock and J is 0, K is 1, what will be the output of the flip-flop? Output of the JK flip-flop for J equal to 0, K equal to 1.
0.
How much? Yes, Sana, how much it is?
0.
0, yes. So that is called as reset state of the flip-flop. Similarly, when you apply clock, J is 1, K is 0. What will be the output of the JK flip-flop?
1.
1. Very good. And this state is called as what? What this state of the flip-flop is called as?
Set.
Set state. Yes, right. And last state, when the inputs are 1, 1, J equal to 1, K equal to 1, what will be the output of the JK flip-flop? Yes?
Toggle.
What will be the Qn plus 1 output?
Qn bar.
Output will be what?
Qn bar.
The previous state, complement of that. So Qn bar, and this state of the flip-flop is called as toggle state. So this is called as no change state. Obviously, if there is no clock, the flip-flop retains its previous state, that is no change state. Even if clock is applied and both the inputs are 0, 0, even then the flip-flop will be in the previous state, that is no change state. When J0, K1, it is in reset state. When J1, K0, it is in set state. And when both J and K are 1, 1, the flip-flop is in toggle state. Toggle means what is the previous state? Complement of that. So previous state we have denoted by Qn, and the next state we have denoted by Qn plus 1. So next state will be complement of previous state. So Qn plus 1 will be Qn bar. So using this truth table, now we can derive the characteristic equation or the characteristic table as well as the excitation table, and using that we can draw the state diagram too. I hope this already you have understood. This I have covered in the previous class. That is about what the truth table of the JK flip-flop. Now, how to derive the characteristic equation for the flip-flop. So to derive the characteristic equation for the flip-flop, so you have to construct what is called as characteristic table. If you construct the characteristic table, from the characteristic table, very easily you can get what is called as characteristic equation. As I already told, characteristic equation is the next state equation of the flip-flop that can be obtained by present state and then the inputs J and K. So based on present state, inputs J and K, we can get the next state of the flip-flop. Right? And whatever the table we get, this table is called as characteristic table, and from this table we can get the equation, and that equation is called as characteristic equation. So what characteristic table consists of? The present state input, that is present state of the flip-flop, or what we can call it as the output of the flip-flop, then input J and K, and what will be the next state or the next output of the flip-flop. So these many things you should have in the table, and that table is called as characteristic table. So from the characteristic table, you can get the equation, and that equation is called as characteristic equation of the flip-flop. So how many inputs are here now? In this table, how many inputs I have shown? Yes. How many inputs are there? Total, these are the input and this is the final output. So how many inputs I have shown totally? 3 inputs. What are those 3 inputs? Previous state or the present state you can call, and J and K inputs. So these I have considered as an input. And what is the output we are considering here? The next state. That's why I told characteristic equation is nothing but the next state equation of the flip-flop. So to get this next state, what all inputs we need? The actual inputs to the flip-flop as well as the Qn, that is the current state or the present state of the flip-flop. So with these 3 inputs now, how many input combinations we can get? Yes. How many input combinations we can get? 3 inputs are there totally. So how many we get?
8. 8.
So those are the 8 combinations I am writing here. Right. This is very important part and very easy in fact. Once you understand, I did not explain for all the flip-flops. Okay. Right. But now writing this column is very important from this what 8 combinations here written. Now what the first input combination says here is, if the present state is 0, if the present state of the flip-flop is 0, and if we give inputs J and K as 0, 0, what will be the next state? That you have to write. So can anybody tell me what will be the next state for the first input combination? How you should get this first input combination? The present state of the flip-flop, that is Qn, is 0, and the 2 inputs J and K are 0, 0. So what will be the output? So for that we should know from this truth table, when both the inputs are 0, 0, what will be the output? You can see here. For when both the inputs are 0, 0, the output of the flip-flop is what? Qn itself. That means the previous state. So what is Qn you are having here? What value of Qn you are having here? Yes? Someone should respond. What is the value of Qn? 0. So if Qn is 0 and input J and K are 0, 0, what will be the next state? Next state will be what? Qn only. So what is the value of Qn here?
0.
0. Like this, very easily you can complete this table. Now, if the present state is 0 and if J is 0, K is 1, what will be the output? You can see here again. J 0, K 1. Irrespective of what is the value of Qn, it gives you output as what?
0.
So straight away you should write 0. It is not depending on the Qn value. Similarly, if J is 1 and K is 0, what will be the output of the flip-flop?
1.
1. So previous state is 0. Irrespective of the previous state, it gives you output as 1. Now the important one, when both J and K are 1, 1, what will be the output? Yes? What will be the output for this case? Here we are having J and K both are 1, 1. So you should see from the truth table, when both are 1, 1, what is the output of the flip-flop? When J is 1 and K is 1, the JK flip-flop toggles. Toggles means what? The output will be complement of the previous state. Output will be complement of Qn. So what we are going to get here? For J equal to 1, K equal to 1. Yes, Aniket? What you are going to get?
1. 1, sir.
1. Why 1?
So because Qn is 0 and then the complement of it will be
and J and K are 1, 1. So J equal to 1, K equal to 1 toggles the flip-flop. So previous state output of the flip-flop is 0. So next state becomes 1. Okay. Next, when J and K are 0, 0, what is the first we have to take J and K and check whether you can determine the output with J and K alone. If not, check the previous state. What is Qn? Now for 0, 0, what will be the output? When
1.
J equal to 0, K equal to 0, the flip-flop remains in previous state. So what is the previous state now?
1.
1. So here you will get 1. Next, j equal to 0, k equal to 1. What
Zero.
output you are going to get?
0.
Irrespective of previous, when j 0, k 1, output is 0. Similarly, j equal to 1, k equal to 0,
1.
1. Very good. And lastly, again we are having j equal to 1, k equal to 1. So what will be the output?
0.
Why 0? Because here for 1 1 I have written 1. And now here again for 1 1 you are telling 0. Why?
So because Qn is 1 and then the top.
Exactly. For 1 1, output will be complement of the previous output. Previous output was 1. Now if we give input as 1 1, we get the output as what? 0. This table what we have got is called as, what is called as? The characteristic table of the JK flip-flop. I hope it is clear. All of you understood?
Yes, sir.
Yes. Sahana, is the table clear?
Yes, sir. Yes, sir.
Karthik,
Yes, sir.
understood? Okay. If this table is clear, now the next important step is to how to get that characteristic equation. So to get the characteristic equation, simple thing, just use a 3 variable k map and get the equation, and that equation itself is called as the characteristic equation. So I will draw here one 3 variable k map. I hope it is visible for all of you. 1, 2, 3, 4. So 3 variable k map I have drawn, and you know that this is 0, 1, 2, 3, 4, 5, 6, 7. Right. Now, what are the 3 inputs you have to consider here? In this 3 variable k map, the inputs that you should consider are Qn, J, K. And what is the output? Qn plus 1. So here I will write Qn, J, K. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Is that fine? Now what I should enter here is just write those outputs. What you have? 0, 0, 1, 1. So I write 0, 0, 1, 1. See how I am writing 0, 1, 2, 3. So 0, 0, 1, 1. Next is what? 1, 0, 1, 0. 1, 0, 1, 0. Fine? Just whatever the table we got, that table I have translated in 3 variable table. Now think like how we can form what? The groupings. What groups we can form here? We have solved so many K-maps, right? From module 2, module 3, module 4, module 5. Everywhere we are going to use K-map. Right? So how we can do the grouping here now? You should do the grouping, the largest possible grouping with minimum number of groups. Right? So what are the groupings that we can do? Yes, Sahil? How many groups we can do here?
So 2 groups.
Which two? Which cells I should combine? Cell numbers are written there.
1, 1 and 1, 0.
1, 1 and 1, 0. Which cell numbers I have given already? 0, 1, 2, 3, 4, 5.
2 and 3.
2 and 3 I should form one pair. Okay. Then next.
This is 4 and last one, sir. Which is
4 and 6. Yeah.
yes.
We can form this and this by what? Folding. You can fold the K-map and you can form. In fact, this group is also possible. You can form the third group, but since already both the ones are covered in some other group, that group becomes redundant, so you should not form that group. Is that clear? So now I can write the Qn plus equation from this. So Qn plus 1 equal to, what is the equation for this group now? This you can see what is the common here. Right. Here it is what we have is J, and this is Qn bar. So I can write J Q bar or Qn bar plus what? Here what is common? K bar. K bar, and what is this?
Qn.
Qn. So this itself is called as the characteristic equation of the JK flip-flop. That is J Q bar plus K bar Q. J Q bar plus K bar Q is called as the characteristic equation of the JK flip-flop. right? This is very important question. They ask like derive the characteristic equation for all the flip-flops. So very easily you should do it. And already told you can expect this question in your second CIE test, right? I hope all of you have got the question bank or assignment, whatever you call for your second CIE test. All
Yes,
of you
sir.
got it, right? So just go through those questions given in the question bank. Not only from your second CIE point of view, those questions are important from your semester end examination too. So if you prepare those questions which are given, you are preparing for more than 1.5 to 2 models, close to 2 models, right? All those questions are important. So you practice, solve them. If you have any difficulties, yes, you can approach me anytime. But I want all of you should solve those questions and be confident about those questions, and easily you should be able to answer any of these questions if you get in your examination. Okay, so any doubts here in deriving the characteristic equation for the flip-flop? Qn plus 1 for the JK flip-flop is JQ bar plus K bar Q. Right? Is it clear?
Yes, sir.
Okay. Now, quickly, we'll see what is the excitation table also for this. Actually, characteristic equation is nothing but what? Getting the Qn plus equation or getting the output equation. Now, what is excitation table is, suppose if you know what is the previous state of the flip-flop and what is the next state of the flip-flop. So, to have the transition from that previous state to next state, what should be the input? What should be the excitation? So, if you obtain that, that table is called as excitation table. So, how we can derive the excitation table? You can see here, as I said, from the Qn and Qn plus 1 value, you know the present state, you know the next state. To get that, what should be the inputs J and K? That you have to find. So 0, 0, 0, 1, 1, 0, and 1, 1. Right? You need to find. So it is very easy now to get the excitation table. If you have this characteristic table, easily you can get the excitation table. Now, if Qn is 0 and Qn plus is 0, what should be J and K input? You can see here, these two cases. Qn is 0 and Qn plus 1 is 0 here. Right? Both are 0, 0. So, what should be J and K inputs? You can see. What is if 0, 0 here? Both are 0, 0. Here also 0, 0. Here it is 0 and 1. That means if you are having the present state as 0 and if you want next state also as 0, compulsory J should be 0 and K can be either 0 or 1. Is that clear? Compulsory J has to be 0, K can be either 0 or 1. So what I should write there? To have a transition from 0 to 0, if present state is 0 and next state is 0, then what inputs I should have? J should be compulsory 0. And what should be K? K can be either 0 or 1. That means K can be don't K. So that is the first like entry in the excitation table. Similarly, when Qn is 0 and Qn plus 1 is 1, that means for these two cases now, there is a transition from 0 to 1. When the JK flip-flop has to make a transition from 0 to 1, what should be the excitation table, that is values of J and K. That means you know the output now, how the flip-flop is changing from one state to next state. To have that change from one state to next state, what excitation or what inputs you need, that you are going to write. Now for this case, you can see compulsory J should be 1 again and K can be either 0 or 1. So what I should write there?
1 and don't care.
1 and
Don't care.
Okay, that is X. Okay. Now the last, that is third case, that is when Qn is 1. Okay, Qn is 1 and Qn plus 1 is 0. That means this and this and this and this. Right? Not the two one after the cases. 1 to 0, here also 1 to 0. In that case, what you can see here is 1 to 0, 1 to 0. Here, compulsory k should be 1 and j can be either 0 or 1. K is 1 in both the cases. J is 0 or 1. So what I should write there? Compulsory k
Don't
has
care
to
and
be
1.
1. J can be either 0 or 1. So x 1. And the last case when 1 1, you can see here, this is 1, this is also 1, this is 1, this is also 1. Now when there is a transition from 1 to 1, you can see compulsory k has to be 0 and j can be 0 or 1. K is 0, j can be 0 and 1. That means k 0 and j can be what? X. And this table is called as the excitation table of the JK flip-flop. So I hope it is clear. I have explained you what is characteristic table, characteristic equation, excitation table for the JK flip-flop. Any doubts here? Yes, Vishal? Understood? Have you understood the excitation table? Snehal? Yes? Ujjwala?
Yes, sir.
You understood characteristic table as well as excitation table?
Yes, sir.
Yes, very good. Anybody who has not understood, you can tell me. I will explain once again if you have not understood. Snehal, what happened?
Understood, sir.
Okay, good. Right. So here in this on this board you can see this is called as truth table of JK flip flop, characteristic table of the JK flip flop, characteristic equation of the JK flip flop, excitation. I have given the entire summary of the JK flip flop. I will give you now a state diagram also. That means whatever the state changes you have shown in the what truth table or the excitation table, you need to show it in the form of graphical representation. I will show the two states, that is state 0 and state 1. This is state 0, this is state 1. Now it will remain in 0 or it will go to 1 depending on the values of what? J and K. Right? So you have, suppose if you are in state 0 and if you have given inputs as what? J equal to 0, K equal to 0. What happens now? That means your present state, QL value is 0. And you have given j equal to 0, k equal to 0. So whether you remain in the same state or you will go to the next state. Because flip-flop will have only two stable states, either 0 or 1. There will not be any other state, right? So now, if the flip-flop is in any one of these states, and based on the input, whether it remains in the same state or it goes to the next state. That we have to represent by a diagram, and that diagram is called as the state diagram. Clear? Now suppose if it is 0, that is presently JK flip-flop is in 0 state, and if we give j equal to 0, k equal to 0, what happens? Whether it will remain in the same state or it will go to the next state, that is one state.
The
Yes?
previous
0
same.
0 if you input, it remains in 0 state only. So what you should do? From this, it remains here only if you give j and k as 0 0. Clear? If j and k are 0 0, it remains in this state only. Now suppose if you give j equal to 0 and k equal to 1, what happens? You are in this state and now you are giving the input as j equal to 0, k equal to 0. So whether it will remain in 0 state or goes to 1 state. Yes? So you have to check what will be the output for j equal to 0, k equal to 1. What is the output for j equal to 0, k equal to 1? Yes, Abhay? What is the output for j equal to 0, k equal to 1? Yes? You are getting it or no? 0. If you give j equal to 0, k equal to 1, then the output of the JK flip-flop becomes 0. That means even then it remains in what? Same state. So for 0, 1 also, not only for 0, 0, for 0, 1 also, it remains in the same state. Right? Okay. Now if you give what? J equal to 1 and K equal to 0. You are in 0 state and the input J is 1 and K is 0. What happens?
1.
1 means what? It will make a transition from this state to the next state. It will come from this state to this for 1 0. That is it. 1 0 means J is 1, K is 0. Right? Similarly, you are in 0 state and if you give both the inputs as 1 1, what happens now? I am in currently 0
1.
state and both the inputs are 1 1. Then, yes?
So 1 again.
Again it once. Why? It becomes toggle. 0 becomes 1. So either 1 0 or 1 1, it goes to the next state. That means what is the summary here? When the JK flip flop is in 0 state and if the inputs are 0 0 and 0 1, it remains in the same state. And if the inputs are 1 0 or 1 1, it goes to the next state. The same thing can you tell me now? You are in 1 state and if you give the inputs as 0 0, what happens? When J equal to 0, K equal to 0, it remains in what? Same state. Next, if J is equal to 0 and K equal to 1, if you give J 0, K 1, it comes to what? Next state. That is for, sorry, J 0, K equal to 1. K equal to 1 resets, so it comes back to this. Similarly, if J equal to 1 and K equal to 0, it remains 1, and if it is 1 1, again it changes from 1 to 0. So whatever the state, whatever the diagram I have drawn with the two state, that diagram is called as the state diagram of the JK flip flop. So any doubts here? Entire summary of the JK flip flop is available on the board, right from its truth table, characteristic table, excitation table, characteristic equation, and the state diagram. So any doubts here? Is that clear?
Yes, sir.
Like
Yes.
if you understood this, like very easily you can derive the characteristic equation, excitation table, or state diagram for the all the three flip flops. Will you able to do that? Yes.
Yes, sir.
Okay. Any doubts? All of you understood it or no? Yes. I say at least yes or no. Whether you understood, entire thing is available there. You can just take the screenshot of that. You will get the summary of JK flip flop, and with the help of this, you can derive it for any flip flops. Okay, fine, good. I can see there are many yes, yes, yes in the chat box. Fine. Now quickly, I'll play one video wherein the similar thing what I have explained is explained for SR flip flop. You can just have a look at it. The SR flip flop is explained here.
Of your SR flip flop and also table for SR flip flop, which is a very important
Okay, so here
one. Now let me tell you about this QN plus 1, because
this
till
is
now we
the
were
characteristic
using
truth table of the SR flip flop which
their
I have
values.
studied.
The next state will be determined. Okay, when clock is high and S and R are 0 0, we know that it is the memory. It is the memory, and by memory I mean that the next state is going to be same as the present state. So the next state is Qn plus 1 and the present state is Qn, and in this case you can see that Qn plus 1 is equal to Qn. Similarly, when clock is 0, it's always the memory, and by memory I mean the next state is equal to the present state Qn. So this is what you have to keep in your mind. And similarly, when clock is high, SNR are 1 1, it is invalid. We don't use this configuration in
I hope all of you know this is the truth table of the SR flip flop. When clock is 0, irrespective of the SR values, flip flop remains in the previous state or the present state, whatever you call. And when clock is applied, when S is 0, R is 0, it remains in the previous state, that is no change. S is equal to 0, R equal to 1, reset. S equal to 1, R equal to 0, reset. It is almost similar to the truth table of the JK flip-flop except for the last input combination. Here the last input combination 1-1 is called as invalid. The last input combination 1-1 is called as the invalid combination. Now for this
SR
you have to
flip-flop,
derive
S is high and R is
the characteristic equation.
out. In this characteristic table, we have to
Okay,
your
so
input
characteristic
is
table you have to write
and
Qn,
also
S and R.
the
Okay.
Qn
Qn,
plus
SR,
1
Qn plus
because
1.
I
That's
just
how I have
told you
written there.
that
Same thing you
the
write here
next
again.
state is dependent on the SR, the two inputs, as well as the previous state. So let's find out the values for Qn plus 1 by using this truth table. There are 3 inputs to it, therefore 8 possible combinations. So let me first make it 0, 0, 0. By evaluating the values for Qn, we are having the possible combinations. Let's try to find out the values for Qn plus 1. The first case, when S and R both are 0, 0. We already know when S and R are 0, and I'm assuming clock is high for all these operations. It cannot be low, definitely the clock is high. When S is 0, R is 0, it's for memory, and by memory I mean that this next state is equal to the present state. So present state is what? Qn, and Qn is 0 for this configuration. So Qn plus 1 is equal to Qn, and Qn is 0. Okay, so this is how we have to do for the rest of the cases. When S is 0, R is 1. When S is 0, R is 1. Qn plus 1 is 0. So simply 0 here. When S is 1, R is 0. Qn plus 1 is 1. You can see from this case. And when S and R both are 1, it is invalid. So I will put a cross mark here.
Yeah, this is important here. When you find S is equal to 1, R equal to 1. In the JK flip-flop, we have written toggle, complement of Qn. But this state is not allowed in the SR flip-flop. It is forbidden. So you put a cross mark. That is a don't care or invalid state. That's what you have
Again,
to
when S and R are 0, memory, and in this case Qn is 1, so Qn plus 1 is also 1, and 0, 1 because SR are 0, 1, 1, 0, and the last case is also invalid because S and R are 1. So you have just evaluated your characteristic table, a very simple one if you know the truth table, and you can see that until unless you know the values of your next state depending upon S and R, you cannot evaluate your characteristic table. So first remember the truth table. Now we will move to our next important table, that is your excitation table.
Okay. So before we see the excitation table, quickly I want you to derive the characteristic equation now. So how you can derive the characteristic equation here? Use 3 variable K-map, write the inputs as Qn, S, R, and write the 8 outputs as 0, 0, 1, X, 1, 0, 1, X. Just quickly, can anybody tell me the answer for the characteristic equation? Before we move on to the excitation table, I want you to give me the characteristic equation for the SR flip-flop. Quickly, just you have to solve one 3 variable K-map. You know these 8 values. These 8 values you have to write there. 0, 0, 1x, 1, 0, 1x. Do it. One of you should do and tell me the answer. Yes, Omkar, you got the answer? Omkar, you are there? Quickly, anybody has got the answer? Seema? I'm asking just to solve one simple 3 variable schema and tell me the answer. What is the characteristic equation for SR flip-flop?
Sir, S plus SQN.
Yes plus?
Yes, into QN.
No, wrong. Check. I think what you have done is you have entered. I'll tell you what is the common mistake people do is here the outputs are 0, 0, 1x, then 1, 0, 1x. I think you have written all these outputs in a sequence 001x, then 101x. But when you draw the three variable K map, the cell number starts with 0, 1, 3, 2, then 4, 5, 7, 6. I think Aditi, you have not taken care of that. Am I right?
No, sir, I have written correct, sir.
First cell you have to enter, that is 0th cell you have to enter 0, then 0, then x, then 1. That is in the first row. Then in the second row you have to enter 1, 0, then x, and then 1. You should not enter 101x as it is because cell numbers are different. Right?
So S plus Q and R dash.
S plus Q and R dash. Yes, that is S plus R bar Q should be the characteristic equation for the SR flip-flop. Aditi, you checked where you have gone wrong?
Yes, sir.
It should be S plus R bar Qn. S plus R bar Q should be the characteristic equation for SR flip-flop. Hope others also will do it. I told you are going to get it in your exam, so you have to practice. Okay. We'll move ahead and see the excitation table.
And in excitation table, the two inputs are Qn and Qn plus 1, and the two outputs are S and R. So we have to find out the values for your S and R depending upon the values of Qn and Qn plus 1. So let's see for the first case when both Qn and Qn plus 1 are 0. We have to see from this characteristic table. I have already told you that the characteristic table is determined by the truth table and the excitation table is determined by the characteristic table. That's why the truth table is the basic block for this table. So Qn is 0 for these two cases, and also Qn plus 1 is 0 for these two cases. And I can see that the value of S is always 0. So I can write S equal to 0, but the value of R is 0, 1. So I can write cross. That is, R is our don't care. Now let's see when Qn is 0 and Qn plus 1 is 1. So I will do it in different color. Here Qn is 0, Qn plus is 1, and in this case S is 1 and R is 0. So S is 1 and R is 0. Now let's move to the next case when Qn is 1 and Qn plus 1 is 0. And for this,
so here you people may be wondering why this fourth case is not considered. Can anybody tell me why the fourth case is not considered here? Why only this like case is taken for 0 and 1? Because this is also 0 and what? X. So obviously that will not come here in Qn and Qn plus 1. 0x state is not there, so we will not be considering this 0x as well as 1x when we derive the excitation table. That is the important thing that you should remember
we are
for the
having
SR flip-flop.
this case Qn is 1 and Qn plus 1 is 0. In this S is 0 and R is 1. So S is 0, R is 1. And for the last case when Qn and Qn plus 1 are 1, which means this case and also this case,
Yes.
the green ones. In this R is always 0, you can see, but S is changing from 0 to 1. So S is our don't care and R is 0. So this is our excitation table. You need to remember this thing because you are going to use it frequently in the flip-flop conversions and also in the counters. So just remember these things, they are very important. One more thing that you have to do here is to find out the value of Qn plus 1. So how you are going to do that? You are going to make
The characteristic equation is explaining.
8 cell K map because 3 inputs are there. So we are having a 8 cell K map. Let me make it. And in this 8 cell K map, you are having your inputs as Qn, S, R, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1 here. Now let's fill this K map for Qn plus 1, 0, 0, 1, cross, 1, 0, 1, cross. Okay, now let's do the pairing. My first group is this, combining two don't cares and two ones.
You can see here, Aditi, you can just observe there.
1. And my second group is this one. Okay, and I will call it 2. So let's find out what is the value of Q1 plus 1. It is 1 or 2. So from the first group, I'm having what? S, because R is changing from 1 to 0 and Qn is also changing from 0 to 1. So it is S. And from the second group, I'm having Qn and S is 0 and it is 1 and R is 0 and remains 0. So S will be neglected and I'm having R complement. So this is the value for Qn plus 1. Similarly, you can.
I hope it is clear. S plus R bar Qn is the characteristic equation for the SR flip-flop. So again, this screen summarizes the complete behavior of the SR flip-flop. How I explain the JK flip-flop, same way it is explained for the what SR flip-flop here in this particular video. So I hope that is clear. All of you understood both the SR flip-flop as well as the what JK flip-flop complete behavior. So any doubts here for SR and JK flip-flop? All of you understood?
Yes, sir.
Okay. So now similarly, can you able to do it for D and T flip-flop? Right? All of you can do it for D and T flip-flop. If you understood both, I have explained JK as well as SR, because here two inputs are there. If you want quickly, we can run through for the D flip-flop also, and similarly then you can try it for the T flip-flop. This is for the D flip-flop. I hope it is
How to
visible.
get a D flip-flop using the SR flip-flop that I made here. I have complete reason for this. I expect
Directly I will go to the
clock is
characteristic
low.
equation.
Whatever be the value of D, your output have the previous. Similarly, when your clock is high, the output will be high. Very like we did in the SR table, we have our output as the characteristic table.
So here, this is the truth table of the D flip-flop. You can see when clock is 0, irrespective of D, flip-flop remains in the previous state. And when you apply the clock, if D is 0, output is 0. And if D is 1, output is 1. This is the truth table of the D flip-flop. So you can see its characteristic table and the excitation table.
The next state will depend on the input as well as the previous state. So our previous state is Qn and the input is D. And my output is Qn plus 1.
In this case, you will get only two outputs now.
Possible
One is
combinations. So
the
let us
input
write
and the
down
previous output.
combinations 0, 0, 1, 1, 0, 1, 0, 1. Okay. Now let's try to find out the value for Qn plus 1 by using this truth table. When D is 0, it means your Qn plus 1 is 0. So it is simply 0. When D is 1, it means Qn plus 1 is 1. So it's simply 1. Again, when D is 0, it's 0. And when D is 1, it's 1. So one thing that you can see from this characteristic table is that your Qn plus 1 next state is going to be same as your D, the data input.
In fact, this itself is called as the characteristic equation of the D flip-flop. If you solve the two variable came up, you can get one pair there and you can get the characteristic equation for the D flip-flop as Qn plus 1 equal to D.
So that's what we have evaluated from our characteristic table. Now it's time to move to our Qn.
Similarly, you can get the excitation table.
Now, by this characteristic table, you can directly write and that how you could have written the values directly. It means, and when Qn is 0, Qn plus 1 is 1, which means, let me change the color, which means this case. And when your Qn is 1, Qn plus 1 is 0, which means this case, again your D is 0. And till now you have seen that D is equal to Qn plus 1 that I have already evaluated. And for the last case also, your D is equal to Qn plus 1. So 1. So this is all about the characteristic table, and it's better to remember that Q1 plus 1 is same as D. And I'm telling you this thing because flip-flop conversions and the you're going to require this knowledge, where if you cannot make your characteristic table and excitation table ask in question, you have to convert JK flip-flop to D. In the next presentation, we have
Okay,
JK
so
flip-flop.
this is about the characteristic equation for the D flip-flop. What is the characteristic equation for D flip-flop you are getting? Qn plus 1 equal to D. I hope it is clear. All of you understood this? All of you getting this or no?
Yes.
Right. So I have explained for JK, SR, D. Now last one is T, the characteristic equation for the T flip-flop. Right. So the
Whenever you
characteristic
listen to a
equation
teacher
for
for
the
startup,
T flip-flop is
presentation.
here.
In the last one, we completed the introduction to the T flip-flop and also found out this truth table for it, in which I'm having the T as my input and clock, of course. When the clock is low and whatever be the value of T, we are going to have the memory because flip-flop is not operational.
T flip-flop, this is the truth table. When clock is 0, irrespective of value of T, flip-flop remains in the same state. And when clock is high, T is 0, even then it remains in the previous state. And when T is 1, it toggles. T0 remains in the previous state, T1 it toggles. So this is the truth table of the T flip-flop. You can get the characteristic equation from the characteristic table. So the characteristic table is,
And when clock is high and T is low, so definitely one is Q and T is 1 and K is 1 as the state was QN last presentation, and we will use it in our following my lectures. Then definitely a flip-flop for D flip-flop knew how to find out the character. Everything
go
that you
directly to
want
the
to
characteristic
derive can be
equation.
derived from the truth table.
You
So
can
let's
derive it
see
from the truth
what is a
table.
characteristic table. Qn plus 1 is my next state, and it depends upon the present state as well as the input. You already know whatever be the value of the next state, it depends upon the input that you are giving to it and in what state it is in. Okay, so Qn and T are the two inputs and four possible combinations. Let's see for the first combination what will 0. It means the
I will
0
write all the
state. Its
combinations.
one is 0, so its complement is 1 is. You are having a characteristic table. So if I say the truth table gives us characteristic table and the correct.
Now use this characteristic table and you get the characteristic equation. It can be shown that the characteristic equation for the T flip-flop is Qn plus 1 equal to T XOR Q. T XOR Qn. You do it as a homework. Just use two variable K map. Enter the values as 0, 1, 1, 0. You will get it as T bar Qn plus Qn bar T. T bar Qn plus T bar Qn. It can be written as T XOR Qn, and that is the characteristic equation for the T flip-flop. The characteristic equation for the T flip-flop can be obtained. You can see there from
So it is what? It is what? It is odd one sector. It is simply
you know
a
that odd
Qn
parity indicator
and
is nothing but the XOR.
T. So this is all for this presentation. Now you are having everything to move.
I hope all the four flip-flops are clear here. Anybody is having any doubts? Right? So in detail, all the four flip-flops are explained. In fact, all the flip-flops are summarized with the help of what is called as characteristic equation, excitation table. Similarly, you can draw that state diagram. That is optional part. If you want to draw the state diagram for all the flip-flops, you can draw the state diagrams too. Right? So with this, we'll close